So now we're going to move on to is basically looking at data that's not, handwritten and you can't just copy it or just write it down, type it in directly, right? We want to be able to open files because a lot of times these will be, 1,000 lines long, 10,000 million, lines long data sets, and you don't want to type that in because you're going to spend, 10 years typing it, right? Okay, so how do we figure out how to open files, okay? Because whenever you have a file, each of the files is going to be a little bit different, and there's going to be a trick to figure out how to open it, okay? So the first trick is to just look at the file with your eyes, okay? It's the eyeball technique. So if you go to your folder where your notebooks are, right? Hopefully you put it in the same spot, and Jupyter Notebook actually allows you to open it. If I can find it, you want to see it? I don't have that much stuff here. Surprised I can't see it. Okay, there it goes. It's all the way on the bottom because it makes it hard to see. Okay. All right. And Jupyter Notebook has the decent text interpreter. It even opens like other types of file like JSON files and HTML files. But if you have like a raw, binary data file, it's not going to be able to open it. So if you just click and open the file, it has a bunch of this information on there, right? So it tells you when the data was taken, what the setup is. There's a bunch of information here, okay? This is information that you need in order to do your lab, okay? This came from the mass spectrometer thing we read about last time, actually, okay? And it's actually row 23, right, where the data actually starts, right? So you can tell it's data because it's just, 1, 1.1, 1.2, 1.3 is the boring stuff, right? Okay? And then there's some numbers next to it, right? Okay, and some of these numbers are negative. We'll talk about what that means, okay, in a second, okay? So it's like, oh, okay, I have a data file. I'm going to tell Python to open it, okay? So in order to open and load a file, NumPy has a functionality called load text. So surprise, surprise, okay? And I just put in the file name, okay? If I run this, so those of you who have the file downloaded and up, just type in, import NumPy as NumPy. You don't even need this yet, actually. I don't know why that's there. Okay. Okay. And if you run this code or you do a Shift Enter, hopefully you get a big red box.
Oh, okay. I'm just like,
Okay. This is where I'm going to teach you how to deal with these big red box, because you're gonna see this no matter who you are. Okay. Everyone sees the big red box. All right. Okay. So a lot of times, right, it's usually the beginning and the end of the big red box that's important. So just look at like maybe the first 3 lines. So it's like value error, right? Trace back most recent last call. I don't know who they're calling. They've been calling their mom or something like that. I don't know who they're calling. Okay. And then value error cannot convert strings to float. APR. What the hell is APR? It's like a month or something like that. Yeah, April. It's like why does it think it's April? This is February. Why does it think it's April? Is this thing crazy? Okay, and I'm gonna skip through all this other crap, right? And then look at the last thing. Okay, value error cannot convert April to float 64 at row 0, column 1. Huh. Okay, so it's having trouble converting April, the month, into a number. It's like, because it's not a number. Yeah, so now if we go back to the data, why does it think it's April? Oh, because the stupid data was taken in April, right? So that's the first thing it sees. So what happened is that Python opens this file. The first thing it sees is April. I don't know what April means. It's not a number, right? I can't put it in an array. So what the first thing we need to do is actually, well, as a data set, we don't want it to store APRO and filament current 1.0 milliamp, all this stuff, right? We don't want that in there, right? So what we want to do is actually have it skip the first 22 rows, right? Okay. And guess what the function to do that is called? Okay, skip rows. Okay, so yeah, you don't need this yet. So what we want to do is actually skip the first 22 rows. Okay, and that way it goes straight, right, to this number, right? Hopefully. Okay, and see what happens. Okay, if you push play on that one, okay, you get a different red box. Okay, the red box is different. It looks similar, right? There's another value error. Trace back most recent call is keep calling as mom for some reason. Okay, all right, and then all of this, and it's telling you this file is not working, right? There's all this, blah blah, site package, all that stuff. Say, what the hell's going on here, right? And then if you scroll to the bottom, right, of the red box, it says could not convert string 1.00 comma to float 64 in row 0 column 1. It looks very similar. Instead of APRO, it's telling me it cannot convert. Well, there's the trace call, right? It cannot convert 1 into a float. Isn't 1 a floating point number? I'm sorry?
It said it was a string.
Yeah, it says it's a string. Why is 1 equal to a string? Well, 1.00 is still a floating point number, right? The comma, it messes you up, right? Look at the data. Okay. The first thing it's reading, right? White space is okay. It's reading 1.00 comma, right? It thinks it's a word, because it's the commas in English, right? This is in numbers, right? But anything that has even one character that's in English, comma, period, well, period is okay because it's a decimal, comma, colon, whatever, right? In fact, the reason why do you think that the comma is there? It's separating the two columns, right? So this is the mass, the atomic mass unit. This is actually the partial pressure of that particular mass unit, okay? So it actually wants to separate these two things with a comma. Unfortunately, whoever wrote this program decided not to put a white space there. So it's now reading this as a string, okay? So how do we deal with this? Okay, we can tell Python, okay, how these numbers are separated. This is known as a delimiter. Okay, it limits the values. Okay, all right. So all the fonts are messed up again. Okay. The resolutions I got. Okay. Anyway, so since we have a comma here, we can actually tell Python that instead of on top of skipping the first 22 rows, we tell them that, the thing that separates the numbers, look for these commas and don't think of it as a word, okay? They are separated by this comma thing, okay? Guess what's going to happen now? It's going to be great, right? Okay, we get a different red box. Okay, similar thing is trying to trace some calls and stuff like that. But the thing is, right, you look at the bottom here. Now it's not converting, what? Converting something, nothing, converting nothing to a float. Why is it trying to convert nothing to a float? On row 0, column 3. Why is column 3? Which, the space should be fine, right? So this is column 1. Now we tell it, okay, ignore the comma, right? And this is going to be column 2. And it's able to take this 1.8 e negative 009, right? This as that e is 10 to the negative 9. Okay, and then there's another comma which it should be able to handle. But then This is column 1. This is column 2. What's the problem here? What's the red message telling you? Column 3. What about column 3? When you put a delimiter like this, it's expecting another number after this, right? But there's no number. That's why it's really confused when it sees nothing when it expects a number, okay? So this is the level of thought process you have to go through in order to teach your computer how to read, okay? All right. So how do we deal with this, right? We know our data only has 2 columns, so tell it to read out only 2 columns. Don't expect a third one, right? So how do we do that? And guess what? Okay, instead of skip row, right? We have the opposite is use cols. Okay, use column. Okay, and since we start counting from 0, you want to have it to use column 0 and 1 and not 2, even though it says 3 up here. Okay. Okay. This is someone from, like, you know, Fortran or 1960s started counting from 1, right? This is actually a disagreement on how they even count. All right, now with that, hopefully it works. Okay. Okay. So now you have the delimiter, the skip row, and tell it to only read out the first 2 columns, right? It loaded the text and put it in a container for you called lab room underscore scan. Okay, there's an underscore there. Unfortunately, the display is not that great. Okay, I see that. Okay, I'm going to have it print, right? It's actually not just 6 rows. It's about like 1,000 rows. Yeah, okay. And it gives you the 2 columns, right? 1.00, well, times 10 to the 0, which is 1, right? But it gives you this negative pressure, right? Negative pressure. Some of them are positive pressure, right? It's above 0 versus lower than 0, okay? So this is due to the fact that the device doesn't measure everything perfectly correctly. So when the pressure is basically at 0, it basically kind of fluctuates around 0. That's why you have these very tiny numbers. This is a nano torr, right? So it's like 1 billionth of the atmospheric pressure, right? So these are actually almost nothing, okay? And it's just a fluctuation around 0. So what's going to happen is that if you leave these negative numbers in there, what's going to happen is that it's going to sometimes mess up your plots, because if you go to a log scale, you cannot take the log of a negative number, right? And it's going to crash the code, okay? So let's not have these negative numbers. What I'm going to do is I'm going to do a fancy super duper for loop, okay? What I'm going to do is I'm going to loop through the entire data set. I want to change this number, right? Whenever it's negative, I'm just going to set it to 0. Okay, so when so I'm going to use the range function. So this is a range from 0 to the length of this data set. Okay, and this is going to be a new thing that I'm trying to teach you guys. Okay, okay. The way that Python organizes thing in 2-dimensional array. This is a 2-dimensional array because it has 2 columns and like 1,000 rows. Okay, okay. So it's gonna, the first index is gonna be the row. Okay, I'll put this space here. Put more space so you can see it easily. Okay, this indicates the row. The comma separates either the row, the column, or, you know, whatever is coming out if you have 3 dimensions. But let's just deal with 2 for now. Okay, the colon in there is telling it, I just want everything. I don't care. I don't care about the range. Okay. Okay. If you don't put the colon and just put like 1 single number, it'll just give you that 1 row. So this is, this 1 column. So this is row, this is the column indicator. I want column 1, but I want all the rows in column 1. Does that make sense? Okay. In fact, what I'm going to do is I'm just going to print it out real quick for you so you can see it. Let's do a little plus. All right, let's print this out. So whenever you're not sure what the data looks like or anything like that, Just print it out. Okay, so this is all the pressure, right? If I want all the atomic mass units, so this is the second this column here, column 1. If I want column 0, right, I just change this to 0, right? It will give me all the atomic mass unit, 1, 1.1, 1.2, 1.3, okay? If I only want the first 10, right, I can just do this, right, from 0 to 10, right? It will just give me the first 10 rows, okay? So you can play around. This is called slicing and dicing your array. So you can cut it up however you want, okay? And this just takes a lot of practice. But the thing to know is that comma, right, separates the dimensions of the array. So it could, this is a 2-dimension, there could be a 3rd dimension, okay? Colon tells you which part of that array you want, okay? All right. All right, so let's go back to what this code is actually doing. Okay, so it's basically grabbing the length of all the pressure rows, okay? Right? This column 1 is just grabbing all of them. It's just asking how long is it, okay? Is it 1,000, is it 100? I actually don't care, right? And for every one of these rows, if, right, that value is less than 1, so this is an if statement, okay? There's also a little colon after this, so it's using colon in 2 different ways, and you have to know what it means depending on where it is, okay? Then, well, I don't want negative numbers, I'm just going to set it to 0. This little algorithm makes sense, right? So I'm looping through the index of all my pressure measurements, 0, 1, 2, 3, 4, 5, right? Okay, right, and it gets replaced here. I'm grabbing one pressure at a time here, right? I'm checking whether it's less than 0 or not. If it's less than 0, I just set it to 0, so I don't have any negative numbers. Now if I print this out, right, notice all those negative pressure is gone now. It's just 0. People happy with this? Let me know if you need more time to try it out yourself. Yeah, Austin?
So in like a lab environment, if we were going to do like statistical analysis on it, if we just set some row equals 0, if we need to remove those negative parts, wouldn't that also affect our, like, if we took averages or standard deviations, because it's counting that as an entry and it's setting it to 0?
Yeah. I think you would. Yeah, so this is just so when I make a log scale plot, this is not going to crash my code. But yeah, if you're going to be like doing histograms of this stuff, which we'll do on Monday, it would affect it. But for this kind of just scatter plot analysis, you're not even looking at that part of the data. So, yeah. Okay. Everybody okay? All right. So, so now let's plot it, right? So in order to plot things, once again, we need this pyplot thing, PLT. Okay. So basically, I loaded the data again, right? And then I did a little for loop to clean it up, get rid of all the negative numbers. And all I'm going to do is just going to plot it, right? And remember when we plot, we put the X stuff and then the Y stuff, right? The X stuff is the atomic mass units, right? How many proton does the thing have as a function of pressure? Sorry. No, yeah, pressure as a function of the atomic mass unit. Okay, so that's why we want the atomic mass units on the horizontal and then the pressure on the vertical. Okay, let's see what this looks like. Okay, and I made it into little dots. Here, let me zoom out so you can see the rest of the code. Okay, sorry, I'm going to reopen this real quick so that it doesn't have this messed up look on it. Yeah, I should just not zoom. My little optimized. Here's all our red boxes. Very important to know how to read red boxes. Okay, there it goes. Okay. So basically, I just I put a bunch of labels on it. Okay. So here's the atomic mass unit, right? The mass of your molecule as a function of the pressure in the room. So if you have a little bump here, but then it goes and goes and goes, so another little bump. And then you have another little bump here at 18 atomic mass unit. And then you have another little bump at 28. And then another one at 32. Okay. It actually doesn't matter what these bumps is. It's just an example. But those of you maybe like taking chemistry might know what these bumps are. Or even not, if you're not taking chemistry, you might know what these bumps are. Why is 28 a special number in air? Anyone know? What's air? What you guys think about it? No one knows what air is? Oxygen and nitrogen. Yeah. What's nitrogen? Well, when you say nitrogen, what do you mean? Yeah, you mean nitrogen molecule, not nitrogen atom, right? And the atomic mass of a nitrogen atom is 14. Yeah, so that's why there's a peak at 28. And guess what 32 divided by 2 is? Is 16, and that's oxygen. Okay. And then 18, I'm just going to give you the answer, is a oxygen with 2 hydrogen attached to it. And guess those are. Right, just water. Yeah. Okay. So you can literally see water, oxygen, nitrogen. There's also this 14 here is actually when you doubly ionize the nitrogen, and you basically split the nitrogen into 2 ions, and then you have 14 here also. The little peak here is actually hydrogen, which is H2. Okay. Anyway, but once the thing, right, you can see that, oh, well, this is really hard to see though, right? Like the numbers down here, you can barely see this, you can barely see this. So this is where I ran into a red box last night because of all those negative numbers. So what we can do is actually put this thing on a semi-log plot. And the way you do that, you basically type in PLT Y scale log. Okay, you just add a line to it. Yeah, question in the back?
Yeah, I was going to ask, since all those peaks are not exactly at the same value, can we get a feel for how much error is present in our system based on the width of each?
Yeah, that's what we were analyzing today. Yeah. Yes, good. Okay. So if you put this on a log scale basically take the 10 base log of the value and put it on the y-axis, but right, it'll label them in powers of tens instead. Okay, so you can tell that this 28 AMU peak is actually about, well, 10 to the minus 6, 2 times 10 to the minus 6, 3, 4. So it's about 4 times 10 to the minus 6. So 4 picobar of pressure. Okay, sorry, not pico, microbar pressure. Okay. Oh, actually, it's in torr. Sorry. Okay. And then the pressure for, what's the other one? 32 oxygen, right, is about 4 times less, right? What's the ratio between oxygen and nitrogen on Earth? About 4, right? But there's also water, right, which also has a high pressure here, right? And as I said, this is 14, which is actually half of this. There's also other stuff. Who knows what 40 is, by the way? A little bit more chemistry. Maybe not. Who knows what 40 is? Okay. Or 2? Who knows what has atomic mass of 2? What molecule? I'm sorry, huh? Yeah, hydrogen, yeah. So 40 is actually argon. There's also one at 44. And the hint is that more people you're in the room, the higher that 44 peak goes. CO2, yeah. So you can actually separate. So notice that by putting it on a log plot, now you can see these smaller peaks much more clearly. But now it's really hard to compare the size of these things now, right? You actually have to really think about, okay, so this is 10 to the minus 8. This is more than 10 to the minus 6. So this peak is actually 100 times smaller than this one, okay? So be a little careful, okay? Okay. You can also zoom into the plot. So I haven't shown you guys how to zoom yet, okay? So what I'll show you is actually plot basically by slicing the array. So what I'm doing up here, right, I basically, you know, loaded the data, made a bunch of labels, and told it to give me every row, right? When you don't put a little anything around this colon, it's telling you to get everything, right? All this first, all column 1, all of column 0. I can actually tell it to only give me elements from 250 to 290, and these has to match with each other, because if you don't have a one-to-one correspondence between your x and y, then it won't know what to do with that, right? If you just give it an x, it doesn't have a y, then you can't really plot it. Okay? Okay. And this is it's a zoom in part around 28 AMU. Okay? Right? Notice that this is 240, this is 26. Okay? The reason for that is because the measurement starts at 1 AMU, so it's shifted by 1 AMU. So it starts, so the x-axis actually starts at 1 AMU, 2 AMU, 3 AMU, but then the index here starts at 0, 0 0.1, 0, 1, 2, 3, 4, right? And there's 10 points for every AMU, okay? All right. Okay. So this here, right, is basically the zoom in part of this peak here. You can actually see the second one around it too, right? Yeah, this, yeah, is that it? No, I think it's this little shoulder here, actually. Okay, so you can zoom in by just changing, right, which part of the array you give it, right? Okay, and that's usually the best way to zoom, because if there's another way to change the y lim and x lim, but then you're looking at certain part, but you're still plotting the everything, so it's kind of a wonky thing. So let's try this yourself, okay? So you guys are already doing your notebook, right? Load the data set. So instead of printing out all the data, like, can you try printing out only the row between 250 to 290, so both columns, okay? And compare the data that you see as numbers to what you see up here. See if it makes sense, okay? See if, like, you know, in the middle somewhere you get, you know, 4 times 10 to the negative 6, okay? 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 Then when you're done with that, okay, all right, so do the same thing as what I did down here, but instead of zooming around this 28 AMU, zoom around 18 instead. Zoom around, look at the water instead of the nitrogen, okay? So let's try those two things, okay? I'm gonna put a pause, okay? So, so we're gonna focus on this 28 AMU. So as I mentioned, this is basically the nitrogen peak, okay? But notice that, right, a nitrogen either has 28 AMU or it's not a nitrogen, right? Or at least that one particular isotope, right? We don't have, you know, 28.1 AMU. You don't have a tenth of a proton sitting somewhere and then attaching it to your nitrogen, right? So why are there values that's not exactly 28, right? Why is it spread out like this? Yeah, so this goes back to the first markdown we did, right, from Monday. So there's an uncertainty on this data because it is taken with a real device, right? Right? So when you do a measurement, right, I think last time we discussed this, right? So the measurement of this mass spectrometer, the radius of that sensor may not be exactly at the right place. The magnetic field or the electric field may not be exactly what their values are supposed to be, right? So therefore you have a spread in this data, okay? And this is where we're gonna deal with uncertainty. Oh, I should have had this picture up, okay? So, you know, so this E field, B field, right? If there's some mismeasurement of this, it'll give you a slightly off measurement. This radius that's measuring where the detector is located, right? What the B field is, all of this is going to cause uncertainty. Okay. In fact, we'll have a little discussion. So in order to do the calculations for the M, right? Last time I think I derived this for you guys, where well, by derive I mean I just did some algebra. Right, I moved the M to the left. Okay. So the M, the mass you get basically depends on the radius of curvature, that's this B prime field, and the speed that the ion is coming out, which depends on the E field and the B field in the velocity selector, right? So this radius, maybe if I do this, it'll make it look nicer. Doesn't this look bad to you guys? Yeah. Yeah, why does it do that? Right. Well, last time when I reopened it, it made it look nice again, I think. Here's the rendering. Okay, let's scroll back down. Scroll. Okay. Okay. So there's your little function. There's an equal sign that's missing a little dash. Okay. So there's uncertainty in the radius of their measurement, right? We're going to call this delta R. Okay. The little delta tends to indicate uncertainties. Okay. And I'm just going to write it. Right. It's like this. Right. It's basically like an 8, but you don't finish the 8. Okay. Okay. All right. The magnetic field that you measure, right, depends on how well you can measure the current through the solenoid that's actually generating this this magnetic field. This velocity v, right, is actually a subset. It depends both on the electric field and the magnetic field. So it's actually it's like another layer of uncertainty buried underneath, right? So there's 1, 2. We're going to ignore the Q for now because the Q is going to be this quantized thing. Okay, we can figure out what the uncertainty in R, uncertainty in B. Uncertainty of V will depend on the uncertainty of E and B. So there's 2 things in there, okay? All right, so we're going to just put delta in front of all these things, which indicates the uncertainty of these things, okay? In order to figure out what the uncertainty on the mass is, basically the spread of this AMU mass that you're measuring, okay, we need to do this thing called propagation of errors and uncertainty, okay? I'm just gonna, so the Taylor textbook, which apparently I lost somewhere, but it may be in the lab. If one of you guys borrowed it, let me know, actually. But in general, if you just look in that textbook, it'll tell you, okay, if you want to figure out the uncertainty of some random variable W, okay, and this W depends on X, Y, Z, K, Y, L, a bunch of variables. In order to calculate what that uncertainty is, you basically take a big giant square root, you take the partial derivatives of X of that function, multiply by the uncertainty in X, you square it. You do the same thing with Y, you do the same thing with Z, you do the same thing with this, K, L, M, all the other letters, right? Okay. So this means you're calculating a bunch of partial derivatives and then plugging it into this equation in order to figure that out. Okay. I'm going to do this the long way. I'm going to show you the shortcut afterward that works most of the time. Okay. But that's why I want to show you the long way, because if you don't know that the shortcut works, just do it the long way to make sure, right? Because otherwise you'll get the wrong uncertainty. Okay. So remember, to calculate the mass, right, we need to know what R is, we need to know Q, we know B, and know V. And for this case, I'm just going to assume all of these is singly ionized, so the Q is just going to be 1. Okay? All right. So the uncertainty in delta M is, there's a big square root up on top of this, right? It's this, if I take the partial derivative with respect to R, right, this is just some constant times R, right? The derivative of that is just going to be B over V. So that's where this partial derivative comes from. Everyone see that? Okay. If I do the partial derivative with respect to B prime, it's going to be similar. It's going to be, it basically knocks down the power of B prime by 1, right? And it just disappears. Okay. But if I do the partial derivative with respect to V, right, the V doesn't disappear because the damped V is in the denominator, right? So you decrease the power of V by 1, which makes it a -2. So that goes in the denominator, and then everything else stays, okay? And just the Q, just make the Q equals to 1, okay? So that's your whole shebang of that partial derivatives. Unfortunately, V is buried inside. There's an E and a B inside, right? There's a B prime field, and then there's the E and B field, right? You go up here to the picture, right? The E and B, the regular E and B field determines how fast this thing comes out. The B prime determines how much of a curvature you get, right? So there's actually two different B's in this place, okay? So in order to figure out the uncertainty on V, right, which is this thing, right, we have to figure out the uncertainty in E and B, right, by taking partial derivative of this stuff again, right, partial derivative of V with respect to E, you knock down this power by 1, you get 1 over B. You take a partial derivative of the velocity with respect to B, you decrease the power of B by 1, so it goes from -1 to -2, so you get 2 powers down here, and the E stays up there, right? Hopefully this is can be done quickly. So now we know that the uncertainty in V as a function of the uncertainty of E and B, and now you can plug this back up here, right? And then you get this giant long equation that sometimes draws correctly, sometimes does not draw correctly. There it goes. It's pretty good now, right? And then you get to plug all this stuff in there. Okay. So for this complicated function, it's actually typically easier to calculate, to actually not just to calculate, to look up from the manufacturer what is the relative uncertainty as opposed to the absolute, okay? The manufacturer will tell you, oh, the uncertainty on this measurement is 10%. So if you measure 10, that means it's either, it could be 9 or it could be 11. So there's an uncertainty of 10% in there, okay? So usually they give you these specs in either relative uncertainty or absolute uncertainty, okay? Absolute means the actual value. Relative is dividing by whatever value you have, right? So in this case, if we divide this whole function by m, right, you know, which is the function we define up here in equation 2, okay, right? A lot of this stuff kind of collapses down to basically the uncertainty, this first term, basically it's just the uncertainty in R divided by R, the whole thing squared. The second term is the uncertainty in the B prime field divided by B, the whole thing squared, and then so on like that, okay? Right? So if you look in this lab manual, actually not in the lab manual, in the additional lab thing that you look up, this rga.m.pdf, they'll tell you what the uncertainty on these measurements are relative to their absolute, okay? So the relative uncertainty on delta R over R is about 0.5%, okay? The B field, all the fields, basically they're the same, is about 0.1%, okay? All right, so if you plug all of these numbers into here, okay, the relative uncertainty combined together is actually 0.0053, so a little bit more than 0.5%, okay? Notice that, right, basically this delta R uncertainty is the dominant one, right? Right, because it's about 5 times bigger than the other ones, right? And then when you square, because you're squaring this, you're basically kind of like having a square power, okay? Since this is 5 times bigger than this, it actually has a 25 times bigger effect on the uncertainty, okay? Right? And then if you evaluate, well, we're concerned with this number at 28 AMU, right? So we just multiply this by 28 MU. So the uncertainty in AMU is actually about 0.15. Okay? All right? So that's the theoretical, that's what the manufacturer claims it should be accurate to. And we can see it, hopefully. Well, we'll see what it is in the data, okay? Okay, the way you figure this out is what we already learned how to do, is fitting the data with the uncertainty to find the uncertainty. Right, so we go back up to this plot here, right? And I think Seth mentioned, right? So with the width of this, right, basically kind of tells you what the uncertainty on these measurements are. Okay? All right, so we go down here. So how do we fit this? Actually, I'm going to have you guys do it. Great, that's even cooler. Less work for me. So what you want to do is basically have your file loaded, right? And, you know, center back around the 28 AMUs part, okay? And then what I want you guys to do is to, from what we learn about fitting that parabola, okay, figure out how to fit this top peak here. I'm going to give you 2 hints because otherwise it'll take forever, right? The fit function, instead of a parabola, is going to be this Gaussian function, and I literally typed out the function in what's it called, in Python code for you guys. Okay. Okay. So this Gaussian function is going to depend on its independent variable. There's always going to be an independent variable, and if you make that independent variable always x, then it makes it easy for you to remember it, right? A is the amplitude, how high that Gaussian goes. X bar is the average value. Basically, if you look up here, right? A is basically how tall this is, right? X bar is where it centers, right? 28, hopefully. Okay. The last one is the sigma parameter, which tells you the width of this. Actually, it's half the width. Okay. Okay. So, if you encode this, and the hint is that you only want to center around the 10 points around that peak. That's why I have you guys do that previous exercise to zoom around. Okay. You don't want to fit this whole thing because this whole thing doesn't fit to a Gaussian, right? To this, because this is not part of the Gaussian, right? Because you should only, the Gaussian will fit like this around it. This is not part of it, right? Okay, so let's see if we can figure out how to do that in about 10, 15 minutes, okay? Okay, so let's keep going so we can kind of wrap up this last discussion. So we're not going to do more technical stuff, but we want to, you know, basically interpret the physics that came out of this, right? Because remember, this is a physics class. It's weird. It's a lot of coding, right? So let's go back down. There's all my red boxes. Okay. So if you made the fit, hopefully it'll look something like this without the little dash on it. Okay. It should fit around the 28 AMU point, and you can draw it in red for me, and that way I don't take off points on your lab when you do this. Okay. So when you do this fit, right, I'll just show you what it looks like, right? So I define my Gaussian here, my param 0, this is 1e negative 6, I just guessed it as like a micro tour, right? 28, hopefully that's why that's a reasonable guess, right? And I have no idea what the width is, so it's like 1, 2, half, you know, whatever it is, right? Well, actually we do have an idea what the width is, right? Which number here corresponds to the width that we're trying to fit to the data? Anyone? Come on, don't stop looking at your computer. It's fine. Your computer will be there. I won't be there tonight, okay? Right. So we actually have an estimate of what that width is supposed to be, 0.15, right? I guessed at 0.5, but you know. So we'll see what the fit tells you. Okay, those of you who are able to complete the fit, right, you can actually print it out just like we did before. So this first number, right, corresponds to this A, which is the amplitude of the Gaussian, right? 4.8 times 10 to the negative 6. So that's actually where this peak is, right? The second parameter, right, is x bar. It's actually not 28. It's 28.95. So we're off by like a fraction of a percent, right? The last parameter is the width that we're actually trying to do this error analysis on, which is negative negative 0.18, right? So this negative one basically shifts this over by 1, right? So in the calculation, right, we calculated it to be 0.15. This is 0.18 with the negative sign. With these errors, it doesn't matter what the negative is because you're always squaring this anyway. So don't worry about that negative, okay? So the manufacturer is, you know, it's not completely lying to us. It's pretty close, right? So that's sort of neat. You can actually confirm that, you know, this uncertainty that you're getting out of the data corresponds to what the manufacturer claimed the accuracy of the measurement of the devices, right? Which is kind of neat. Okay. So with that, what I want to just wrap up today is kind of like how do you kind of write this up in your result discussion, right? So we did the whole analysis. So the analysis kind of ends here, right? Now we're going to talk about the result discussion in your notebook, okay? So, let's read through a little bit of this, right? So this is just me talking to myself, right? There's a lot of this in your notebook. The idea is that you're talking to yourself, making sure that, a week from now, right, you're able to write the lab report on it and remember what you did. And then maybe like a month from now, oh, if you need to do this lab in the future, how do you do it, right? And it's interesting how many times like I wish I kept my notebook from my undergraduate lab. There were so many cool labs I did as an undergraduate, but then I didn't keep the notebook because I was moving around a lot, and then I just threw a bunch of stuff away. Anyway, so that's just my regret. But since you guys are doing this digitally, so you don't even need to keep these notebooks, right? Well, the computer keeps the notebooks for you. Okay, so this is the result discussion. So basically, is that, well, you're discussing what you see in the data. So the data from the lab room's analog scan, and tell us which data file you're looking at, right? It's plotted on the cell above, right? On the notebook, you can refer back up and down, right? Because it's in the same notebook, so I can see it right above it, okay? And the fits agree with the data on the left-hand side. This is actually sort of interesting, right? You can actually discuss this, right? The left-hand side fits the data pretty well, right? The right-hand side is actually off, okay? It's interesting observation. Oops, come back down, right? And but the right-hand side seems to be too high, right? The red is too high compared to the data, right? So somehow there should be more pressure on the right-hand side, right? And I'm just going to guess, oh, the difference between the left-hand side and right-hand side is that there's actually this additional 29 AMU peak here that's smaller than the 28. And did I already tell you where this could come from? Why is there something that's 1 AMU off of your molecule? So nitrogen is a 14 nitrogen molecule is a nitrogen atom stuck together with 3 bonds, right? Okay, there's 14 each. It should add up to 28. Why would there be a 29? An electron doesn't have that much mass. Extra what? Extra what? Extra okay, you're diving really deep. It's an isotope which has an extra what? Extra proton will change the charge. Extra neutron, yeah. So it's an isotope. So there's a nitrogen 15 are in here. In fact, if you compare the heights of these peaks and you just Google search the abundance of nitrogen 15 versus nitrogen 14, this will be the ratio you get. Okay. All right. Anyway, so this is something you can look up, right? And then you can look up, isotopes of nitrogen, right? In fact, I think that ratio is about 0.4%. Okay. So the ratio between these two peaks is basically a factor of 20. Is that right? No, sorry, factor of 200. Yeah, off by an order of magnitude. Okay. The log, you see how this log plot tricks you, right? Because this is down here, so this is already order of magnitude 10. This is about 100, and then a little bit is 200. Okay. Anyway, so this is the little discussion. So about these, what you're seeing in the data itself, what makes sense, what doesn't make sense, right? The left-hand side makes sense, the right-hand side didn't make sense. Why is that? Oh, there could be this effect from this extra peak from here, right? Okay, because the left-hand side didn't have it. Okay, discuss what the data is about. Look up additional information as you think about them. Okay, and then you basically have kind of a numerical analysis of what you see, right? We estimated the uncertainty from the manufacturer's specification to be about 0.15 AMU, right? That's from this analysis all the way up here you did in your notebook. If you want to just write these equations down and take a picture of it and post the picture, that's fine. I don't expect everyone to be, super into LaTeX coding if you don't want to. But you do have to document what you're calculating in the lab, right? Okay. But then experimentally, right, we measure this, right? So this fit value that came out, right? You just, for a lot of uncertainties and fit value, uncertainties on value, just do 2 sig figs at most. Don't do like 3 or 4 sig figs, okay? And then the central value should be as good as the uncertainty. Okay, so let me just tell you what that means, right? In case that kind of got forgotten from general physics, right? So let's say I have a number, right? Number 18.2, 3, 4, 5, 6, 7, you know, whatever. But I know this number is only good to plus or minus 0.1, right? Okay. Okay. So I only know this number up to 21. So these digits are completely meaningless. So when you write the result for this, you write 18.2 plus or minus 0.1, right? Hopefully that makes sense. Okay. And then for the uncertainty part, which is the sigma thing that we're talking about, right? Right? Keep 1 or 2 digits. Don't keep like 10 of these, okay? Because when you print it out, right, I don't want to see all this crap, right? Right? Because anything after 0.1, basically 0.18, doesn't matter anymore, right? Okay. All right. So, yeah, so that's why I write 1.118. So the percentage difference, this is the, I don't know if this is the first time you're seeing percentage difference. Have you seen this before, I hope? Right? You're calculating what the theoretical value is, which is 0.15, because that's the manufacturer specification. What you actually measure in the lab, you multiply by 100%, so this actually turns out to be negative 20%. I know that some people put an absolute value sign around this for this class. Don't do the absolute value sign, because the sign actually means something. Okay? This means, right, the manufacturer is underestimating their uncertainty by 20%. Right? If this was a plus, they are overestimating their uncertainty, right? Okay, the sign actually has physical meaning. Okay, and the central value for the X bar, right, is this 28.95, right? Since I kept this number up to the 100th place, I'm keeping this number up to 100th place also, right? And then the value of the uncertainty is this, and you know. And if we compare, because technically it's supposed to be exactly 28, right? So we're actually off by 0.2%. Okay? So this is kind of like the result discussion you want to put in your notebook. Right as you taking the measurements. Whenever you have a result, write it down, think about it, talk about it. Okay? You're going to have time in lab. Okay? So each lab is going to be 3 weeks. Okay? You're going to maybe spend the first week trying to get the damn thing to work. Second week, you're going to be taking data and doing this sort of stuff. And the third week is going to be writing and finishing up and the peer review. Okay? So you have time. Okay? Yeah, I'd rather you guys do lab very well versus doing a lot of labs. So it's opposite of analog and digital, I guess. Okay. So the assignments that's going to be due on Monday. So there's going to be a little bit more because you have the weekend to do it. Right? So basically, you know, do all the stuff that we've been doing in class. And then there's a few more problems posted on Canvas. If I can show it to you guys. Right? So this is the lecture 3, right? So this stuff you already did. This stuff you already did. Why is it like this? Okay, oh, because I copy and pasted this, okay? And then I just have you guys play with arrays, right? A little fun with arrays. Do a little nuclear physics, right? And then also do a little bit of sunspot, do a little bit of astronomy, and that's it, okay? So it's basically like 3 additional problems on top of what you started in the class already. Okay? All right.